Gnanam paramam dheyam. Knowledge is supreme.
In the last lecture, we have seen that for every finite field extension, the embeddings of this field extension inside an arbitrary algebraically closed field extension, this number, the number of embeddings, is bounded by the degree of the field extension, and this number is also independent of the choice of the algebraically closed field extension of K. So, let me write in symbols what we have proved. We proved if you have L over K finite field extension, and E over K arbitrary algebraically closed field extension, then the number of K embeddings of L in E, this number is bounded by the degree of the field extension, and this number is independent of the extension E over K. So, that means this number depends only on L over K, and therefore, this number, we define this number to be separability degree of L over K. S. S is in the notation here. This is called the degree of separability of L over K. That is the definition of. Now, we will prove that we will observe some basic properties of this separability degree or degree of separability, and we will prove that equality happens if and only if the given field extension L over K is separable. That is what we will prove. So, we are aiming to prove this is a numerical criterion for the extension to be separable. So, some properties. Some properties of this L over K sep, this symbol. Some people also denote this symbol in a different way. For example, one notation is L over K sep for separability, or also one denotes it by simply by E L over K, this E being for embedding, cardinality of the embedding and so on. But I will stick to this notation, but these are also used. Okay. So, the first property we have already observed, if L over K, if L is simple extension, simple, finite simple of course, simple algebraic extension of K, then this Kx over K, this sep S, this is nothing but cardinality of the zeros of mu x K in L, in Kx. That is the number of distinct roots of the minimal polynomial in Kx. This was precisely done when we did zeros and embeddings. So I want to recall, this is what we have done in the when we were discussing in the lecture, zeros and embedding. In that lectures. So that was one. Second, if we have field K contained in M, contained in L, finite field extensions, then the L over K S is M over K S times L over M S. This behaves like a degree, so like multiplicative. So let us prove this. So proof of proof. Let E over K be an algebraically closed field extension. Then we want to understand what is an embeddings, how many embeddings are the K embeddings are there from L to E, and what is that relation with embeddings of K M to E. This, and obviously embeddings of M to E, M to E, L to E. Let's see, we want to understand these two sets and we want to relate their cardinalities. So first of all, look, there is a natural map here. This, remember, embeddings is a K algebra homomorphism from L to E. These are K algebra homomorphism from M to E. All are fields, and these numbers will not depend on the algebraically closed field that we have chosen, that we have seen already. So if sigma is from L to E, this maps to sigma restricted to M, because if sigma is from L to E, then I just restrict means this is from M to E. And this is obviously surjective, because if I have an embedding from M to E, I just okay. So remember by Steinitz theorem, that tells, if you call this map, I want to call this map, what can I call it, alpha. The map alpha is surjective. How does it follow? Let us indicate that is due to Steinitz theorem. You see here you have M here, M to E we have, and they are K embedding, means they are K linear, that means this diagram is commutative. So we have given this here tau, and L is here, this is, and this extension is finite, therefore algebraic. And Steinitz extension theorem says that whenever I have an algebraic extension and K algebra homomorphism inside an algebraically closed field, then I can extend it, sigma. That precisely means this, whenever I have given an embedding of M in E, I can extend to L. So that means this map is surjective, that is from Steinitz extension theorem. Now both are finite sets, both these are finite sets, because their cardinalities are bounded by the degree of L over K, and this cardinality is bounded by M over K, and L over K is finite extension, therefore both are finite sets and surjective map, and therefore if I want to infer about their cardinality, I should know what are the fibers. So what are the fibers? So fibers of alpha. So what does that mean? That means if I fix tau, so for a fixed embedding, K embedding tau from M to E, I want to know how many extensions are there. So that one for a fixed tau and sigma belongs to the fiber of tau, that is if and only if sigma is an extension of tau to L. So in the diagram, that means given this, I have L here and I extend it to here, that is sigma. So the number of sigmas I have to count. Okay, but therefore the cardinality of the fiber is precisely extensions from M to L. So that is if and only if this sigma belongs to embedding over M of L to E. If I fix this tau, then this sigma is uniquely determined by, so this means what? This means okay, so we have so this means, now note, this is from set theory I want to recall. This means, so suppose we have two sets X and Y and a map between them alpha, and suppose this alpha is surjective and all fibers of alpha have same cardinality, both are finite sets, and suppose all fibers have the same cardinality equal to R, then how do you compute the what is the relation between the cardinality of X and cardinality of Y? Then we know cardinality of X equal to R times cardinality of Y. This is very easy to see. And we are in the similar situation. We know that this alpha is surjective, and I want to relate the cardinalities of these two sets. That is why I wanted to know what are the fibers, but fibers are in one-to-one correspondence with the embeddings of L to E over M, and therefore we know cardinality of embeddings of L into E. This is same thing as cardinality of the fiber, that is cardinality of embeddings of L over M in E times cardinality of the image where it is. So embeddings of M into E. But these are precisely, what are these precisely? These are precisely L over K S equal to, that is L over M S times M over K S. So that proves, this proves 2. I just want to remind you here that though I wrote this if and only if sigma belongs to the embedding over this, so this is quite it is little bit this is the little bit abuse of notation, because all that we know is sigma is an embedding of tau to L. So this is actually, one should write it here that it is embedding of, this doesn't depend on the tau, so it's independent of the tau. So all fibers have the same cardinality. So I will just caution here saying that, check this. Okay, so we have proved that the degree of separability behaves like a degree. All right, now theorem I want to prove is, so theorem we want to prove is, let L over K be a finite field extension, then L over K is separable if and only if L over K S equal to L over K. So equality hold. So look at this side, right side is just a numeral, two numbers are equal, and that is separability, which is defined in terms of every element. So that is the advantage. So proof. All right, so first let us prove this way. So we want to prove that, assuming this equality, we want to prove that every element is separable. So let X be an element in L. We want to prove it is separable. To prove X is separable over K. All right, now we know that, so look at, we are in this situation, K is here, Kx is here, containing L is here. So we have this tower of field extensions. Therefore we know L over Ks equal to Kx over K S times L over Kx S. This property 2 I am using, and this I know it is equal to L over K given, and this we know it is Kx over K times L over Kx. Now this equality is given, so from there I infer that the equality holds at each one of them. So therefore Kx sep S equal to Kx over K, simply because we know this is smaller equal to this, and this is also smaller equal to this. So if it is, both of them have to be equal to this, because if one of them is smaller, then the corresponding product will be smaller. So therefore this, and we know what is this. This we have proved, this is nothing but the number of zeros. So this is V of mu xk L, this is Kx. So that means this is the number of zeros of the polynomial mu x in this, but that will mean that the number of zeros. So what do we want to prove? That these are distinct. So we want to check that. So to check that X is separable, we should check that mu x over K is a separable polynomial. That means it has the number of zeros is exactly, if you take in algebraic closure, the number of zeros of mu xk is precisely the degree of that. So, but this is the degree of mu xk, and the separability degree is what? Separability degree is precisely, so I don't use this. The separability degree is the number of embeddings of kx inside an algebraically closed field. This is algebraically closed. And how many embeddings are there? They are precisely the number of zeros in mu xk, the number of zeros of mu xk in E. That is because, so the each zero we can define a map, and conversely each, this we have proved earlier, this is proved earlier. Therefore, this cardinality is equal to this cardinality of the embeddings, which is by definition separability degree, and separability we have proved this equality, but this is the degree. Therefore, this number equal to degree, so that means mu xk is separable. That means this mu has so many roots in E. So we have proved this. So therefore, we have proved one way, that if equality holds, then it is a separable extension. Conversely, so this way, conversely we are suppose that L over K is separable, then I want to prove that the equality degree of separability equal to the field extension degree. Alright, so L is finite separable, therefore L is generated by finitely many elements x1 to xn, and each x1 to xn is separable. Over K. All elements are separable because the field extension is separable and is finite extension, therefore it is generated finitely many of them. And now I am going to prove this assertion by induction on this n. So we will prove by induction on n. On n, what will we prove? That this L over K sep equal to L over K. This is what we want to prove. So look here, K is here, L is here, K x1 to xn, and then we have M inside. M is just one less, K x1 to xn minus 1, and this. Now I have the tower of field extension, and this L is M over xn. Now this is separable, therefore this extension is also separable, and this also is separable, because xn is separable over K, therefore xn is separable over M, because mu xk and mu xm, what is the relation in general? If you have a subfield in between, then this divides this in mx. That is the relation. So divisor of a separable polynomial is always separable. So because of that, both these extensions are separable. Therefore, by induction, I would have had proved that M over K S equal to M over K, this is by induction, and also L over M S equal to L over M, and then you multiply them out. If I multiply this out, we have proved a property that this product is same thing as, so LMS times M over Ks, this is equal to L over Ms. This is by property 2 we have checked, and this is by induction, it is L over M times M over K, but this is L over M, L over K. So therefore this equal to this we have proved, and therefore we have proved a theorem that the extension is separable if and only if degree of separability equal to the degree of the field extension. All right. Now I want to prove so-called primitive element theorem. So the primitive element theorem, actually we have proved a weaker theorem than this. We have proved a primitive element theorem for Galois extension, but we don't have the assumption that extension is Galois, but we only know extension is separable. So let L over K be a finite separable field extension. Then we want to prove that then there exists X in L such that L equal to Kx. So that means that is X is a primitive element for the field extension L over K. It's a simple extension. All right. So how am I going to prove this? Well, I am going to prove this by using the embeddings. I will use embeddings to choose this element X correctly. I may recall that in case of Galois extensions, we have also used elements of the Galois groups. We thought them as linear maps, and then, so what was the proof for Galois if L over K is Galois? I just want to recall that. I want to imitate the ideas. If this was Galois, then we looked at the Galois group, Gal L over K. This is a finite group. So if you have an element sigma in this, so that means the sigma is K algebra homomorphism from L to L, K algebra automorphism actually, and therefore it is linear map from L to L, K linear map in a finite dimensional vector space. So we looked at the kernels of the sigma, and they are, if sigma is not identity, these are proper subspaces of a finite dimensional vector space L. This is a n dimensional vector space where n is the degree of the field extension, and we have chosen an element outside the unions of this kernel, and that gave the primitive element. So similar thing I am going to do it for the we will use the embeddings. So this we will do it after we take a break. We will continue this proof, and as a consequence we will prove that an extension, finite field extension, is Galois if and only if it is separable and normal. This was what another equivalent definition of the Galois extension. So we will do this after the break. Thank you.